Hey everyone, today we're going to look at Unit 3, Lesson 2, and this is all about kind of scaling and scale factors again. The concept here is that we are able to look at different objects that share certain properties, and we can compare them using ratios or fractions. So one that we all have to make sense of is the way that when we look up in our sky, right? We see there's two objects in the sky most often. That's our sun and our moon, right? And we study these objects for many different reasons, but what we do notice is that when they're in the sky, they don't appear to be that different in size, right? We see a difference, and yes, sometimes it'll be a little bit different, right? Sometimes the moon will be bigger than other times for sure. The sun's about always the same size in the sky, but we notice that they're small. They're not taking up the whole space, and but we also know that the sun is much further away, right? It's like 83 million miles away, right? It's super far. The moon is much closer, right? It's our moon, right? But so why is that the case? Well, it's because the moon is smaller, but it's much closer. And the sun is much larger, but it's much further away. And so this type of comparison and this type of um, looking at ratios allows us to see why they may happen to be there. Because in fact, the moon size divided by the sun size, sorry, not liking my writing today. That's going to be the same as the moon distance to Earth divided by the sun's distance. That is, of course, when they have the identical sizing to us in the sky, right? That's when that happens, right? Is when this equation equals itself. And this is one that we can look at because again, they take the same shape. They're both spheres, right? Or mostly spherish, right? But this is something that we can compare, right? So what we're looking for is a way to set up a ratio to compare things, right? So we can take one comparison. So again, we can compare size to size, like we can compare distance to distance, right? And so this, when we have the same size in our sky, this should be true, right? Again, because we can compare them in this way. So if we have figures in geometry that are said to be scales of one another, or they are said to be, the word is similar, we can create ratios the same way, right? And so let's look at this. So it says, what scale factor takes a parallelogram C to parallelogram D? Again, quite simply, for our scale factor, we're going to do new over old, right? Where do we end up and where did we start? You could think of this as end over beginning or start, right? So if we look here, it says takes parallelogram C to parallelogram D. So this is a start and this is an end, right? So we're, again, going to expect here, this is a number that's going to be probably a fraction less than 1, right? Because it's shrinking, right? Remember, this is multiplication. So we can get smaller with multiplication if we multiply by a fraction that is less than 1, right? So again, we are going to look to compare similar parts, right? Left side versus left side. So this would be 27 over 45. Okay, end over start, right? Or new versus old. Now this can be simplified, but this is actually going to be the same as 9 over 15, right? That should be the same, again, because it's the same end part over the beginning part, right? Again, as long as we are comparing corresponding parts, we should be fine here. This can actually be simplified even more. Again, we could divide both of these by 3. We could divide these by 3. This could be the same thing as 3 over 5, right? So again, you could think of this is 3 nines over 5 nines, or this is 3 threes over 5 threes, right? Either way, the end result is 3/5 of the original. So not quite half, but fairly close. Okay, so let's look at this, right? So hexagon U is a scaled copy of hexagon T, right? So this is the start. This is the end, right? The end is the copy, right? So the question here says, what is the value of V, right? So we have this unknown here, right? We know that it's going to compare to part the 25, okay? We know that it should be larger than 25 because hexagon U is larger. Now, how much larger? We have to figure this out. So what we need to figure out is the scale factor, okay? That's what we need, is what scale do we multiply by to go from start to end? How does this work? All right, so there's a couple of different ways that we can do this. I'll show you how I would approach this problem. What I would say is we can do all of the work kind of at once. What we need to understand is just like the sun and the moon, if we link together these corresponding parts, we can build an equation that we can use to solve. Okay, so the first one, again, we're going to do end over start, right? Or old, new versus old. So I'm going to do 16 over 10 is going to equal V over 25, right? So those two ratios have to be the same. So there's multiple different ways that we can think about this. The most straightforward way that is going to work in the widest number of situations is called cross multiplication. Okay, cross multiplication. When we have two fractions that equal each other, what we can do is we can cross through the equal sign and actually multiply these items. So we can get 16 times 25 is equal to 10 times V. Okay, right? This always has to work. This is basically a shortcut for finding common denominators. But again, this has to be true if the equation is true. 16 times 25 is 400. This is 10V. And then we can divide both sides by 10 and get V to be 40. Now let's check that answer. Does that make sense? Right? So 40 is definitely bigger than 25. It's not quite to double. So it actually looks like a kind of a nice number here. Now this isn't the only way to do it. You could have seen that maybe like 25 is 2.5 times that of 10. And 40 would be 2.5 times 16. Right? You could have found it that way as well, but cross multiplication is always a good way to go about these problems. Again, we have to make sure we set it up correctly. Once we go there, then we could use our algebra tricks. Okay, so what about this, right? So quadrilateral N is a scaled copy of quadrilateral M, right? So this is the end and this is the start, right? So what do they want us to do here? It says, what scale factor is going to make this happen, right? Takes us from M to N. Again, it doesn't really matter which way you go. They are going to be the same because of that, right? So what we do here is we're going to say, okay, well, 11, or sorry, we'll do our product here, We're going to say 8 times our scale factor is going to equal 11.2, right? It doesn't matter which one you pick, right? It doesn't matter. What you're going to do again is build this equation, right? Start, you take the start, you multiply it by a number, and you get the end. So in this case, S is going to equal 11.2 divided by 8. Now I'm going to use my handy dandy calculator, which is somewhere, to do this. 11.2 over 8 is 1.4. Okay. If it asks you to write this as a proper fraction or an improper fraction, we can always convert this in some different ways. This would be what's 7/5, right? But again, 1.4 can also be just fine, right? So it's just a number, and it makes sense. It's bigger than 1, just a little bit bigger. So we have a little bit bigger object, not so much bigger. Okay, so how do we deal with this if we have word problems, right? So there's going to be some word problems here. So Brenna measured a city and made a scale drawing. In real life, the neighborhood is 132 yards long. It is 44 inches long in the drawing. What scale did Brenna use, right? So how does this work, right? So she's asking, okay, what is, if 1 inch compares to how many yards? Okay, so we're going to build this equation here, right? So it says in the problem that she uses a 44-inch model. So we put the inches on top because that's the way that the question is asking about that, right? So we want to make sure they're in the same position. And then it says we have 132 yards here. Okay, so this ratio has to be held in order for it to be a scale model, right? So again, there's multiple different ways that we can approach this problem. Again, I'm going to recommend the most general way is going to be to use the cross multiplication method. Anytime you're missing one of these pieces, just cross multiply. We don't need to have the units anymore. Okay, we can just use the numbers. So we're going to get 44 times our unknown. And you could give that a name if you want, like X or A, is going to equal 1 times 132. We can divide both sides by 44, and we should get that our unknown here, in this case, the number of yards that Brenda uses, or like what helps with the scale, is going to be 132 over 44. And this, if you type in a calculator, will simplify to just 3, right? So an inch for her is actually 3 yards in real life. And that kind of makes sense, right? Like if you're drawing a neighborhood, right? You want it to be, you want to be able to draw it 3, an inch being 3 yards. That way, a foot would be 36 yards. It'd be pretty big. It's almost 100 feet, right? But again, we just build an equation with 4 parts, one ratio versus another. Last example we'll look at is maybe a little bit more complex one. Again, if you're unsure about any unit conversions, always just you can look it up on Google. But it says Katie measured the elementary school and made a scale drawing. She used the scale 7 centimeters to 5 equals 5 meters, right? So she's not saying that 7 centimeters is 5 meters. She's saying the scale is 7 centimeters to every 5 meters. It says, what is the scale factor of the drawing, right? So how does this connect? Okay, so again, what is the scale factor? So again, this is going to be a scale factor that, because she is making a scale drawing, it's going to be less than 1, right? So it's going to be like 1/10 of the size, or hundredth of the size, right? It's going to be much, much smaller. So we're going to put the smaller units on the other ones, right? So what is this scale, right? So 7 centimeters versus 5 meters, okay? So what we need to be able to understand is, in this case, we need to figure out how to make these the same measure, okay? We need to convert either centimeters to meters or meters to centimeters. Either way, we will be fine, but we just need them to line up. What I'm going to do is I'm actually going to convert the meters to centimeters, okay? Um, so 7 centimeters is on top. This is the same as 500 centimeters. Right? There's centi is 100. Right? There are 100 centimeters in a meter. So 5 meters means 500 centimeters. So this is close to our answer, right? So we're not going to use this because this can be, no, this can't be simplified actually. So this would be 7 to 500. So again, 7 doesn't go into 500 and there aren't any other factors of 7. So we can't really break that down anymore. Again, if you don't know the measurements, just go and look them up. That way you can kind of convert between them. But again, this equation holds because the units I changed, right? I changed meters to centimeters. And that way, when I do that, I can drop this off and I'm just left with the raw conversion, right? At first, when I compare centimeters to meters, I'm not, that's apples to oranges, right? They're not the same thing, right? So just be careful with that when we get to some of these more advanced questions.